Alrighty, today we're going to be talking about percent composition and empirical and molecular formula. So what is percent composition? Now, percent composition is the percent by mass of each element in a compound. So if you want to find the mass percent of something, you take the mass of the element divided by the mass of the compound and you multiply that by 100. The mass percents of all elements in a compound must make up 100%. So you can't have 99.3%, you can't have 98%, it has to be 100% because we're talking about all the elements in the compound. They should total up 100% of what's in the compound. And it can be calculated multiple ways, using the mass of the substances, if you're given them, or the chemical formula. And by that, I mean the atomic and molecular weights. So let's look at this. Percent composition is based on the compound you were looking at specifically, not just the elements it's made up of. So for example, if I have potassium chromate and potassium dichromate, both of these compounds contain potassium, chromium, and oxygen. But they contain them in different amounts. Potassium chromate, its formula would be K2CrO4, whereas potassium dichromate would be K2Cr2O7. So the amount of potassium, chromium, and oxygen in each of these compounds is going to be different in terms of its percent composition. For potassium chromate I guess I forgot to put in numbers here. For potassium chromate, you can see that the chromium takes up less space or less of the amount than it does in dichromate, which makes sense because in dichromate you have two chromiums, whereas in potassium chromate you just have one chromium. And the potassium takes up I'm looking at oxygen here. Oxygen takes up less in the chromate and more in dichromate, again, as expected, because you have more oxygen in dichromate than you do in chromate. And then the potassium looks like it takes up a lot less in dichromate because you've gained so much more chromium and oxygen that the percent composition decreases a lot. So it's no longer that there's just do the math, 7 things in there and you've got 2 of the 7 things. Now there's 11 things in there and you've only got 2 of them. So the amount of potassium in there you see decreases in a dramatic fashion when you add more elements of something else. So let's look at how you can calculate this. You can do percent composition from mass data. Chemists will often synthesize compounds and then have to use analytical techniques to determine the mass of each element in the compound to see if the mass percent is correct. And so, for example, if a 13.60 gram sample of a compound containing only magnesium and oxygen decomposes to make 5.40 grams of oxygen, what is the percent composition? From this, you can see that the mass of the compound is 13.60 grams. The mass of oxygen is 5.40. We can determine the mass of magnesium and use this to find percent composition through subtraction. So 13.60 grams minus 5.40 grams gives you 8.20 grams of magnesium. Now from this, we can figure out the percent of magnesium in the compound by taking 8.20 and dividing it by the mass of the compound, times it by 100, so you get 60.3%. You can do the same thing with oxygen. Take the mass of oxygen divided by the mass of the compound, multiply by 100, and get 39.7%. Okay? So you can do it from actual masses of elements and compounds. Or you can do it based on the chemical formula. In this case, what is the percent composition of oxygen and iron 3 chromate? The first thing you need to do is figure out, well, what's the formula of iron 3 chromate? Iron 3 chromate is Fe2CrO4 Now, then you're going to need to figure out the molecular weight of iron 3 chromate. And so you've got 2 irons, 3 chromiums, and 12 oxygens. Once you add those all together, you get 459.67 grams per mole. Now, in order to figure out the percent composition, you just take the oxygen and you take the mass, the total atomic mass of oxygen in there. So the atomic mass of oxygen times how many oxygens there are, divided by the molecular weight of the compound, times by 100, gets you 48%. Okay? Sorry, let me go back. So you can look at the chemical formula and take that data and just kind of do what we've been doing when we've been doing mole conversions and calculate mass percent like that. Alright. We can also use percent compositions to help us with unknowns. We can utilize this information to determine different amounts of compounds given the amount of others. So what is the percent composition of a compound formed when 2.70 grams of aluminum combine with oxygen to form 5.10 grams of aluminum oxide? So again, you're going to have to use the masses to figure out the mass of the unknown, here oxygen. And then you can figure out the percentage of each element involved by taking the mass of the element divided by the mass of the compound and multiplying it by 100. So in this case, it's going to be 52.9% aluminum and 47.1% oxygen. Now, why the heck are we doing this? What does this tell us? Number one, it tells you the percent composition, which is kind of cool information to figure out. You can know how much of an element is in a compound. But you can also use percent composition to find the chemical formula of compounds, which is important. When solving for the chemical formula from percent composition, there's two different formulas that you can solve for: empirical formula or molecular formula. Now, empirical formula is the smallest whole number ratio of elements in a compound. So that's the smallest whole number ratio of elements in a compound. And the molecular formula is the actual number of each atom in the compound. So it's not just the ratio, but it's the actual specific number that you have. So for example, both ethine and styrene have an empirical formula of CH, where the smallest whole number ratio is 1 carbon to 1 hydrogen. But ethine has a molecular formula of C2H2, and styrene has a molecular formula of C8H8. So they both have the same whole number ratio of carbons to hydrogens, so 1 to 1, but in styrene, you actually have 2 carbons and 2 hydrogens. I'm sorry, in ethine, you have 2 carbons and 2 hydrogens, but in styrene, you have 8 carbons and 8 hydrogens. So, two different things. One tells you what's the ratio of elements to each other in whole number, smallest ratio, and then the other one tells you, okay, but actually how much do you have present? So determining the empirical formula. If you're given the percent composition of the compounds, you can do it like this. All you do is assume 100 grams of the substance. So 40% of an element would be 40 grams of the element. So you assume 100 grams, so 100%, 100 grams, 40% is 40 grams. You convert the grams of each element into moles. Then you divide all the moles of each element by the smallest number of moles found in the compound. This is going to give you the whole number ratios. If the given mass of the compound and then if given the mass of the compound and then the elements, follow the same procedure except that you get to skip the first step where you assume 100 grams. So this is kind of confusing, so let's look at an actual example. What is the empirical formula for a compound with 40% carbon, 6.7% hydrogen, and 53.3% oxygen? So I'm going to assume 100 grams, so 40% of carbon becomes 40 grams of carbon. Multiply it by its molecular weight, and I get 3.33 moles of carbon. 6.7% hydrogen becomes 6.7 grams of hydrogen. Multiply by its atomic weight, and you get 6.65 moles of hydrogen. And 53.3% of oxygen becomes 53.3 grams of oxygen, times it by its atomic mass, and you get 3.33 moles of oxygen. Now, the smallest number of moles for this is going to be 3.33. So we're going to divide each of these by 3.33. So 3.33 divided by itself is 1. 6.65 divided by 3.33 is 1.997, which is approximately 2. And then 3.33 divided by itself is again 1. So since these are all whole numbers, I don't have to do anything. If hydrogen had spit out something closer to like 1.5, then you would have had to multiply them by 2 to get it to its closest whole number. So, but if you multiply the 1.5 by 2, then you have to multiply everything else by 2. So we'll do some practice with that. But my empirical formula then becomes CH2O, where I have 1 carbon, 2 hydrogens, and 1 oxygen. And so that's my smallest whole number ratio for this compound. Next, we can determine the molecular formula, and you do the following steps. You calculate the molecular weight of the empirical formula. So in order to figure out the molecular formula, you have to have either been given the empirical formula or have to have been given the means to calculate empirical formula. and then you calculate the molecular weight of that empirical formula. You've been given the molecular weight of the compound. You should then divide it by the molecular weight of the empirical formula, and this is going to give you a multiplication factor to multiply the empirical formula by to get the actual amount in there. Now, the key thing to remember here is that this multiplication factor should be a whole number. So if you're ever forgetting which one are you dividing by which, are you dividing the molecular weight of the compound by the molecular weight of the empirical formula, or what? Just remember that the bigger one should go on top because you want a whole number that for your multiplication factor. So let's look at an example. What's the molecular formula of a compound with an empirical formula of CH3O and a molecular weight of 62 grams per mole? So carbon is 12.01 grams per mole, so we're going to find the molecular weight of the empirical formula. Hydrogen is 1.008 grams per mole times 3, and oxygen is 15.999. If you add all that together, you get 32.033 grams per mole. So 62 is larger than this, so we're definitely going to be dividing the molecular weight by the molecular weight of the empirical formula. So you take 62.0 divided by 31.003, and you get 2. This is the multiplication factor. So we're going to use this number and multiply the empirical formula by that to get the molecular formula, which now becomes CH3O becomes C2H6O2. Okay? All right. So we're going to be doing a lot of practice with this tomorrow, so come in ready to learn. Thanks, guys.